So here we are, Java, additional topics for FRC session 1. And this evening's topic, of course, is PID. Our schedule from October to February, I've shown this slide pretty much every week, and we're now in the kind of the intermediate and advanced topics. Maybe those words are not the best. They're just, I'm calling them additional topics because they're of varying level of difficulty depending on who's doing the programming and what experience that person may have. And the outline of this evening, well, the topic for this evening is PID control. And the question is, if you want to have your robot move smoothly and efficiently, well, then the suggestion is that we use PID control. And the PID control is illustrated a little bit here in the little diagram. And there's a lot available online about how to do the PID. Now we see several little graphs here, and it's interesting that we might explore them. The square graph, this is the reference graph. This is in a perfect world where there's no momentum, there's no delay, everything just happens instantly. So at time 1, we want our robot arm to move to a distance of 1 radian or something, or to move 1 meter away, the whole robot or something. We want something to move by a unit of 1 in whatever direction or quantity we're measuring. And ideally, there would be no oscillation. It would just go there instantly and there would be no error. So the theoretical world is great. And I studied theoretical physics and we lived in this world and we were happily ignorant of all the life that happens that gets in our way. Friction, momentum, all kinds of things stop us from being able to make a perfect world like that imagined by the physicists. And so when you try to heat something up, for example, my 3D printer is a perfect example. My 3D printer will go to 210 degrees and then shoot right past it. And then after a while, the 3D printer system says, oh, wait a second, we're above 210 degrees. And so it turns off the heater and the heating stops. And then we go down and it goes right down below 210 degrees. And we have what's called hysteresis. And the reason for the 3D printer having quite a pronounced hysteresis is perhaps because of the delay. There's a little bit of a delay between when you turn off the temperature and when the system measures a different temperature, because the heat has to propagate through the aluminum material in the 3D printer. Now, similar issues happen with robotics, and depending on the accuracy and timeliness of your sensors and your programming and the like, you could get something of a hysteresis. So one thing that can be happening, you're measuring and measuring, and the idea is this: let's keep the power on until we get above 1. And then momentum is carrying us, oh, let's turn the power off. And then it's coming down and we're going to turn it on again when it's below 1. But by the time it gets below 1, it's taken a little bit of time and we're getting what we call hysteresis. So you could get a hysteresis that damps out like this one, or you could get just a steady hysteresis. And on the 3D printer, we can have a perfect sine wave of the temperature as it oscillates at 1 or 2 degrees above and below 210 degrees Celsius, at least on the 3D printers I was using. And now there are mathematical ways that we can anticipate things, and we can start turning down the power a little as we get closer to the magical distance of 1. And so you see these other graphs here are a little smoother, and they approach 1 in various ways, either oscillating around 1, or in the case of this red curve, just approaching 1. So PID control has 3 components. The first is the proportional, and that's just the measure. It's based on the measure of how far are we from the desired temperature or output. And then the power being issued to the actuator, such as the motor, is determined according to this proportional sort of measure. So if we're far away from our desired measure, we have a lot of power going on. But as the error decreases, then we reduce the power linearly or otherwise to make the actuator start to slow down and more smoothly attain its final desired measurement. So we also have these other two parts that are used in PID control. Integral, a simple way of saying this is a sum of previous errors, and it involves integral calculus, adding the area under the curve. And we're adding up the previous errors in the measurement, the errors being what's the difference between our current position and our desired position. And that helps us to smooth it out. And then another aspect of our work that helps us to smooth out these curves is the derivative. What is the rate of change of the error from last measurement to the current measurement? So this can be a very technical sort of topic, and you can deeply explore the mathematics. But we'll see this evening, it is possible to set it up without too much in the way of mathematics. And I've set up a very simple PID sort of model. And in fact, I actually have more of a PD model. I've taken out the integration as that was recommended in the FRC website. And I'll show you where we can find out more information about all of this. So in summary here, you see at the bottom, we've got a mathematical model based on calculus. And hopefully when we're done all of this, we're going to get smooth motion in our robots. I better check here if we have any more in the waiting list. No, that's good. Sometimes I miss that. And also we'll just do a quick check on the chat here. We have a chat message. PID, yes. So proportional, integral, and derivative components in an error correction mathematical scheme to make your robots work smoothly. And we'll take a little bit of a look at it right on the next slide here. So what we do in PID modeling is we apply some power to our actuators, such as a motor, and how much power is determined by the sum of three mathematical terms, the proportional, the integral, and the derivative terms. And each of these terms has a constant, and this constant K is a typical letter we use to denote a constant, and there's a K for the proportional term, a K for the integral term, and a K for the derivative term. You will see on the first website and on other sites that it is possible to simplify this down and use just one. Not going to get into the mathematics of all of this. And it's not really important, these constants here, as we're going to only be developing two of them this evening, and then we can do some trial and error to see how we can improve on the values of these constants. In scientific and engineering circles, there's a lot written about how to determine these constants for a system. They're just some constant that works depending on the physical attributes of the system that you're using. Perhaps the mass of the arm of the robot or the mass of the robot itself as it's turning. And you can develop mathematically and using some physics, some good approximations to these constants, but it doesn't have to be that complicated. You can also use trial and error. It turns out that each of these constants is a positive number, and you can try a few values, 1, 10, 100, 1,000, and fairly quickly zero in on the sort of right magnitude for the constants that's going to get the job done reasonably. We'll see this with our little model. All right, so some model code here. This idea we can illustrate using a simulated gyro on a FRC robot. So I'm going to show what we're aiming to do and then explain and develop, well, what all of this is all about here. So here is a little program. It's one of the programs we developed in a previous session in December. I think it's called Simulator 6. It was probably developed in one of our sessions in December. And if you recall, to run the simulator, then we may use Control and Shift and P and simulate our code on the desktop. And I pick these two extensions and run them, and I get a little window for my robot simulation. So there's my robot in the bottom corner there, and I'm going to run the autonomous routine. I have overwritten the autonomous routine. All you're going to see is the robot is turning, and then it stops. And that's our aim. How can you make a robot turn to a certain angle and say, that's the angle we want to be pointing? And that's where we're going to be aiming this evening. So we can discuss a little bit of the connection between your physical robot and this robot turning to a certain direction and then heading in that direction. Okay, so that's our aim. And I've just demonstrated the program working, but now how was the program developed? So we'll go back in here and take a look at some of the elements that were included. So I have some sort of warnings here. The reason is I took out some of the autonomous routine, and so those parts are no longer used. And instead, I've put in a call to import the simulation. And in here, we can, the gyro. And now I had never done this before this afternoon. And just a little bit of trial and error. I tried to import the gyro directly. And then I had forgotten that it's actually not a physical gyro that we're using. So this didn't work out. And then I did a little research and I found out that there's a simulated gyro and some other simulated hardware available through this simulation library. So this is the simulated. Well, when I first tried running the program, I had just a gyro, a regular gyro though, and then the program stopped immediately and said, we can't find any real gyros here. And it was right, because there was no real gyro. And so to overcome that, I've included this library. And now how do we declare the gyro? So I'm just adding a few lines here and there to the existing simulation program. And I went down into the next section here where we have our class constructor for our robot class. And you'll note I'm just using the timed robot. I'm not doing the control-based robot here. And I added a few little items into our code. Right here, I found a type called analog gyro simulator, or it's called analog gyro sim. And I called it gyro, and I made a new one, and I put it on channel 0. And I just guessed that channel 0 based on previous coding on our other robot where we had it either on channel 0 or 1. Put a new simulated gyro on channel 0. And that's just something I picked up before in other years when we were using a gyro on our robot, that it needs to attach to a channel, and I guessed channel 0 and it let me, so I was fine. Now I declared an angle where I would like the robot to head. So to which angle should the robot turn? Maybe that's an even better way to express this. To which angle should the robot turn? And it turns out we're going in a clockwise direction. I should be able to change some of the code here to get a negative 235 going the other way. That's an arbitrary angle. I can change this to anything I want. For example, I could say 335 degrees, and if we run the simulation again, it will turn almost all the way around, but not quite. Don't know why you would want to do that. This is probably more convenient. Turning less than 180 is probably convenient because you'd probably turn the other way if you wanted to go more than 180 degrees. Okay, and I declared a few variables here. One, I need to keep track of the current error and the previous error. And the error is the current angle measure and the desired angle measure, the difference between them. We'll see that in the code. So the difference between the current angle and the desired angle is a double number called error. And this is the error from the previous iteration. Now, what do I mean by iteration? This robot is running code, and the autonomous and or teleoperated modes involve executing that code maybe 100 times a second. And so each time it goes through the code, it will calculate the error. And the very last thing it's going to do before it goes to the next iteration is record the previous error to remember it for the next time around. And we're comparing the errors, and then we're going to do a calculated change of behavior based on the errors. Right now I have two values, the KP and the KD, the derivative and the proportional errors, not errors, the constant. So this one is called the derivative constant. And this one is the proportional constant. And they did not recommend using the integral constant, so I didn't put one in. And I've tried various versions or amounts for these constants. I'm going to try a smaller amount. See how this one works. And we'll see the differences in these values here. I've also been arbitrarily making the constants the same. Anyway, we'll see how they work, and we may be able to adjust them and find a better way for this to get the robot turned as quickly as possible. Okay, so here are my constants, and there's the error and the angle I'm seeking, and I defined a gyro. All of this is in the class constructor. And this source code I'll make available later if anyone would like to see it. Now we may go down here and see where the simulator has been overridden. In the autonomous initialization, when I start the autonomous routine, this part executes once. And in here, I executed two commands: reset the gyro data. And in troubleshooting, I forgot about this. I forgot to set the angle to 0. And if you don't do that, it will stay, or it will maintain the previous angle measurement from wherever the robot was pointing at the end of the previous work. And then the routine will not work as expected. So it's good to reset your gyro. And these turn out to be a little bit different than the methods that we use with the actual gyro. I remember using with the actual gyro the method called reset instead of reset data. And so that's something worth noting, that this is not exactly the same as a physical gyro, but similar. And you do have to do a little bit of research and find the methods that are associated with a gyro sim, analog gyro sim, and note that the methods are similar but distinct from an actual physical gyro. Okay, there's the autonomous init routine. And now the autonomous periodic. This executes repeatedly. Okay, so this code is going to be repeatedly operating or executing. And here's what's happening. First of all, we'll calculate the error. How far are we from our desired angle? So there's the angle we're looking for, and there is the gyro's current reading. So we're calculating the error, and then we're outputting the error, the angle, measured angle. There we are. And you'll see some output will be in our terminal. And then we come down here. I did not put this in our slideshow you'll see here. I've taken out the print statements and just focused on the main code. All right. Now V, I'm setting this here, but I actually may not have to. I'm saying that the robot is not going to be moving forward or backwards. The forward motion is 0, and so is the backward motion. And here is my calculation of how quickly theta should be changing, meaning how quickly should the robot be turning. Its current turning rate is going to be proportional to the error times some constant, the proportional constant, and then the error minus the previous error. How quickly is the error changing? That's the derivative, and multiplied by the derivative constant. And so this comes directly from some equations that we see that deal with PID control, and they're readily available online. So I am going to now drive my robots turning according to this d theta, the rate of change of theta. And you'll see it's driving forward at a speed of 0, and it's turning at d theta. And I've put in a few corrections here. It is quite possible, especially if my Kp value and my Kd value are too high, then it's going to exceed 1 or exceed -1 in the negative direction. And so these two corrections here make sure that I can only set values between 1 and -1, because that's what the motor is expecting. So we're going to cap output at 1. So it's being capped on either end at 1 and -1, so that the robot will not have an illegal value sent to the motor. Okay, and here I'm printing how quickly the robot should be turning. And here we instruct the robot to move. So in a little bit of shorthand, so it's going to move forward at setting V between -1 and 1, and then turn at setting d theta, the rate of change of theta, or the angle. And that's it. The final thing to do is remember the current error as the previous error. And then we're going to continue and repeat. So there's our code. And I just annotated the code a little bit here, so it kind of makes sense. I'm making a connection between the PID and the code here. And again, I have not gone too much into the mathematics. Suffice it to say, this is the most mathematical of the expressions. And it's some constant times the error plus some other constant times the change in error. And that's it. And these are two arbitrary constants that we can sort of play with. So you will note a few moments ago, or a few minutes ago, I changed these constants to 0.001 each. And let's see what the simulation shows us when we try that out. So now I'm executing the code. And We have our autonomous routine here, and you'll note it's kind of changing very, very slowly, and it's going to stop at, what is it, 135? There, 135 degrees have been taken. So that's really slow. Let's maybe adjust it a little. Let's make it 0.02 each and see if that makes any difference to the motion of the robot.
William, is that from the starting point, like however you orient it? It's not from some set axis. It's from however it's positioned, right?
Yeah, it's from wherever it happens to start. I think there's a default starting direction, and we're turning 135 degrees positive, measured from our starting position. Right. And the starting position is kind of arbitrary. I don't know how the system decided it was kind of pointing, was it sideways or down or up? Let's see where it's pointing here when I run this. Autonomous, there we are. Yeah, I was pointing kind of to the right. And then it just runs 135 degrees and stops. So I don't know if I answered your question though. Was that Yana?
Yes, you did. Yeah, and that's what I was wondering is if there's, I guess you could have it use sensor input to determine its starting position and then build an if-then series.
Yeah, and here is where it just sets the sensor input to wherever we're pointing now, that's angle 0. And that's in the autonomous init. So that's important to note because the gyro, it remembers where it was pointing from a previous execution of the program, even when you run the robot the next time. So
is that only in the simulation or is that true of our actual robot?
In both. And I think if you don't initialize it, it may be at just some angle. So it's important to initialize it and reset it and just set it up properly so that it's able to execute as expected.
Yeah, that seems really important. Yeah, okay, good to know.
And it could be a very good troubleshooting thing because one missing statement will make it look like the gyro isn't working at all, whereas it's just waiting to be reset. So I remember that was one of our troubleshooting issues in previous years. So what I was just doing there, I'm just playing around. I just tried a different combination of P and D. In fact, I wanted to do this and just see what that does to the robot behavior. At a certain point, I will also note that the robot's going to be turning too quick, or the calculated values are too high and they're going to be capped at 1. So right now I'm looking here, and the calculated values are very low. And I should have run that again. It's happening so quickly. As I was mentioning it, the calculated value is now hovering around 0 because I'm pretty much reached my angle. Maybe I should set the robot to turn a little more so we can see that happening. Let me just set the desired angle above 180 degrees, maybe 435 degrees. It's going to turn around more than once and then settle somewhere. And we'll try that again. So we have a little time to see the PID loop in action. Okay, so we will look now. I'm going to try to just show the output here. In this output screen, we will be able to see the value being sent to the motor for the turning. Is it fully 1 or is it less than 1? And I believe it's going to be less than 1 at the moment because my K values are rather low. So let's just try that. Autonomous start. And it's at fully at 1, but then as we get closer, it's coming down. So that's kind of interesting. I didn't really note that because we're far away. It was greater than 1, but as we started to approach our target, it became less than 1. And that's exactly what should be happening in the PID. So yeah, that's very satisfying to see that. Oops, and there we go, stop that. And right now it is so close to 0, may as well be 0. Some practical. Oh, go ahead.
Yeah, what if you reverse these P and the D, like put the P at the 0.1 and the D at the 0.004?
Let's try that. Nothing like some experimentation. Here we go. And autonomous. It's kind of going slowly. It's already slowing down. So an interesting thing, that actually makes it less efficient because it was not achieving its full speed throughout a lot of the turns. So as you see there, it took a little longer for all of that to happen. So it definitely can use a little bit of tuning. If I put this up to 0.4, my guess is it's going to be a little faster. Let's try that. So another both 0.04, and we'll try this here. And it's 1, and it's starting to, yeah, it went a little faster. So you'll see that this number here at the bottom.
I'm getting some lag, so just I hadn't seen it. Is it still running now?
Yeah, it's running, but it's now achieved its
angle
goal. So let's try just running that one more time. See if you can catch that. Oops. Oh, what did I do? Okay, try that again. Okay. So we're looking down here for how much power is being put into turning the robot. And we're looking here for the robot turning. And when it's about halfway through its turn, it's slowing down its rate of turn because it's starting to approach its target. And that's exactly what should happen in PID. The trick then is to adjust these K values so this happens as quickly as possible without burning out the robot and without overshooting. Because a robot with lots of momentum, you could turn really quickly, but then it's going to be turning so quickly by the time you get to your target, it goes right past it. All right, so let's just try this here. There it is, and slowing down. And then it's going to stop, getting slower, 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 and it stops. Okay, it turns out I can make these numbers much higher. I'm going to make each one of them 100 times higher just to accelerate through this experimentation. Let's see what happens in this case. My theory is that it actually, because I've made them so high, it may actually be applying 100% almost all the way through the turn. That's my theory, but I actually didn't get to test it until right now. And it's 100%, 100%, and getting closer. It only starts slowing down right at the very end. And here's one interesting thing that we need to remember. This is a simulation, and if we haven't put into the simulation the angular momentum or the angular moment of the robot, which is how much it likes to stay turning or stay not turning. It's kind of like a mass, but in a circular motion kind of sense. If I don't put an accurate value for that, then this looks great. But if I tried this in practice, my guess is the robot would turn right past the desired angle and be halfway around again before it actually even slowed down. So these numbers appear to me to be a little bit high. So the simulator will only get us so far until we actually put in details into our robot about its actual mass and things like this. This simulation is set up so that you can input the angular moment of the robot. And I haven't actually adjusted it at all. So it could be because this robot is not actually behaving like I remember an actual robot behaving in terms of the time for things to happen. So this simulation is only getting us so far. So when you try this PID on a real robot, you may remember that.
Yeah, because the real robots don't turn on a dime, right?
They turn really quickly if you let them. Much faster than we saw there.
Yeah.
So you have to be very careful. Unless you limit, a lot of teams like to limit the output and they multiply, say, by 0.7 or 0.5. So the robot can only go so fast without running over stuff. It took us a while to learn that on our team, and we ran over a lot of stuff at 100% speed. So a good idea to limit your robot's output. So anyway, this PID is definitely useful for your team to achieve some smooth operation. Now there's lots of more resources than what we see right here. Just bring up a few such resources. The way that I find them, I just like to do this first. Robotics Control System 2022. I've already searched for that a few times, and it just tends to come up here. And oh, maybe that's not the best one. In previous years, that just came right up. Maybe I'll try this one, WPI lib. There we are. And programming your robot. Now, the topic is in some of the more advanced controls section. And here we are is a section on control system basics. There's a nice video on PID offered by a professor at Worcester Polytechnic Institute that wrote WPI lib. So that's a really great video to watch. And then there's an introduction to PID with some mathematics. It gets quite technical, using some integrals and some derivatives. So if you're not familiar with calculus, though, you'll note that all of this is kind of simplified down, and we are not doing the full calculation. As you saw, I just had two differences were used for each one of the terms. This E at T is the error, the difference between what I'm looking for and where I am now. I didn't even do the integral term. And then I've calculated the rate of change of the error, which is on the first approximation, the difference between the previous error and the current error. So we simplify all this calculus down to two subtractions. And that hopefully will make the mathematics very manageable. So that's yet another thing that we used to do in physics quite a lot. We had these little tricks to take complicated math and make it much more simple. So don't let this equation be daunting, because what we did with it, we simplified it by taking only two of the three terms. And then the two terms that we have are both based on a subtraction, no heavy mathematics at all. And this is just theory. And this is excellent, though. I do recommend that calculus students should study this. And it's a really great way to understand how derivatives work and get us into other concepts and topics in more advanced engineering and physics. Okay, so there's a lot of discussion of the PID here, but in practice, as you saw, it's a few lines of code and two subtractions. And I was hoping to do that just to show that it can be a little bit accessible. So some great additional reading. I also looked online, though as a teacher, I would never accept Wikipedia. That definitely does have a great article to get you started. And if you want more authoritative resources, there are always those at the end of articles on Wikipedia. So that's another place that I looked. When I look for stuff just to get a start on things, I find Wikipedia is a great place to begin. Many more resources there online, though, and lots of YouTube videos as well. So hopefully this will help the teams in being able to create a robot that operates more smoothly than would otherwise be possible. PID Control. So there we are. Just going back here now. Let's just review a little bit of the computer code that went into this PID. All right, so as you recall, there were a few places in the program where I took the simulator that we already used. And first of all, I imported this simulation.star, and that contains simulated gyro. Then in my constructor, I added these commands to start a new gyro. That command's actually the same line there. And then I defined a few variables, which you saw us use the constant for the derivative and for the proportional part of our PID control. You'll note that 10 is way too high, and something less than 1 was working for us much better than, say, the value of 10. There's the error and the previous error. I just started them out as 0 as they start working as we do our calculations. And there's the angle I was aiming at. And of course, if you want to go to 235, why not turn the other way? So you could probably set up the code with some negative signs and head in the other direction instead. Okay, so there is the code that comes at the beginning of the program in the import section and in the constructor section. Now we go to the part here. I didn't put this on the slide, but this code appears in the autonomous periodic. And in the periodic, I calculated the error, and that's the difference between the angle and the gyro. I ended up putting a minus sign there. I should probably have just subtracted the gyro minus the angle. I also set the forward motion to 0. This can still work even when we're moving forward. Maybe we can try putting the V to a value that's not 0 and see what happens. I defined my rate of change of the angle for the robot. How quickly is the robot to be turning? And there's my mathematical expression, which is one difference. The error is a difference between these two, and another difference, the difference between the current error and the previous error. So complicated mathematics down to 2 constants times 2 differences. Then I adjusted my output to be a maximum of 1 and a minimum of -1 so as to keep the system happy. It doesn't want its motors overpowered. And did a few prints along the way, but essentially I sent a forward amount of 0 and a turning amount to my drive system. And then before we go to the next iteration, we just remember the current error as the previous error and repeat. There we are, that's our PID model. And there's the code, how it ended up going into the program. So how do we experiment with it? We tried this, we just adjust KP and KD. There are methods for doing this online, you can research them. Throwing darts at a dartboard is a good place to start. But there are also some systematic ways online to get it better. So you can try those. And then once you've changed these values, you just try it in the simulator, see how it works, and then repeat. That's the simplest way, but there are much better ways to do this mathematically. It depends on the mathematical level that you have. This could be done by almost any student, but there are ways to do that involving calculus for the students who are studying such topics. So either is accessible for your team. It's an open-ended learning problem. All right, and the references, a lot of them came from the competition control system. I did mention looking online and finding YouTube as a good place to start, with a number of other references in that YouTube article on PID. In my slideshow here, I should also have included the section that had to do with the autonomous initialization. And that's right here. I will probably update the slideshow before we upload that, because I did put a few commands here to reset the gyro. All right, so there is our PID system. And this is just for a gyro. There are other ways that PID could be used to maybe settle upon an exact sort of distance. We could link our PID to our encoders and just driving forward, for example, and we could do a whole bunch of stuff. So one thing maybe we can try, let's make the robot drive slowly forward, like maybe 0.3, while it's attempting to find that angle. And we can try this here. Just run the program as it is now. And so you'll see that this hopefully should work even when the robot is kind of driving forward. Maybe that's a little too slow. I'll try another value, maybe 0.6. There, now it's driving a little bit more, sort of driving around. And I'm just getting curious. I wonder what that looks like when we have full speed ahead. It may actually circle right outside of the field. I'm not sure. Let's see what happens. The circle should be of a larger radius now. Yeah, it kind of went partly out of the field. There we are. That's it. Oh, that's interesting. Because it stopped turning, then it continued forward. That's an interesting side effect because we never told it to stop turning. Or so we never told it to stop moving forward. So theta reached its equilibrium level, and then it just kept on going forward. Interesting sort of things that you can experiment with. There we are. So I think that's a good place to stop here. And be very glad.
I have a question. I
Sure.
know there's a, is that this PID is really mostly useful for autonomous? Yes, not so much for teleop?
I believe like I can see it being used in two situations, definitely autonomous as you saw. However, I can imagine, for example, if I wanted to shoot a ball in driver operated mode, but I want to do it without being all awkward about getting my robot just perfectly lined up. And by the time I get it lined up, someone runs into my robot, which is going to be an issue this year, like many other years. So I can imagine making a state machine, which would do this. Step one, find the target. And maybe my robot is kind of lined up, but not perfectly lined up. So the camera is showing slightly to the left. There's the target, and it should be exactly in the center. So since it's slightly to the left, we can use a PID to smoothly and efficiently turn that robot so that it lines up right in the center of the camera, saying, wow, now this robot is pointing directly at the target for shooting the ball, for example. Okay, so now we know that it's pointing directly there, and I've pressed one button, and it immediately proceeds to fire up the shooter motor, and then the indexer motor just slowly goes and then fires off two balls to the target. So that can all be done with one press of a button, and that's using a state machine. And we'll discuss state machines and how we can incorporate them into the code later in a future session. So I think the short of this is, yes, you can use this in simulation, but it could also be equally used in many situations in driver-assisted mode. I also see there's a question here, how to set up the simulation. So that would be a good thing to review at this time to see how did we get this code here. It's actually not so many steps. So here's what I'll do. I'm going to start a new program and then make a new simulation. Okay. So for a new program, our friend here is our command palette, Control and Shift and letter P for palette. And my most frequently used commands are the first two here, create a new project and simulate a robot, or at least lately. So here's for creating a new project. We can select a project type. And in this case, I'm going to make an example. Is that it? Whoops, am I forgetting? Maybe it is. No, it's an example. We'll go back here. Try that again. Not a template, but an example. And it's a Java example. And we have quite a list of Java examples. If we go right down to the end, or near the end, we should see simple differential drive simulation. So let's try that one. There we are. And I'm going to make a base folder for that simple drive simulation. And here we go. Maybe I'll put it in the Java FX folder. There we are. And oh, that probably is not the best place for it. Maybe, yeah, drive simulator. Yeah, this folder is probably better. Okay, so it's going to be in my Java folder. And I'm going to put it in this folder and select a new folder. There we are. Project name, drive simulator. I don't know what's the number now. I'll just say 5. Maybe I should look, but I'll hope that drive simulator 5 hasn't been taken. There's my previous team number. And because we're doing a simulator, we need to enable desktop support. It says that right here. Simulation support requires this to be checked. So once we've done all of those choices, we can generate this new sample project, and we're going to open it in our current window. There we are. And we have all the code for the project here. If we look in our source folder, we will find under the Java subfolder the files required to run this simulation. Let's take a look at our robot.java. There we are. This is the basic robot.java. It comes with just a little autonomous routine to follow a trajectory. Now that's a topic that's also treated in our documentation, in the WPI lib documentation. So it's going to follow a particular trajectory, which is defined right here. It starts with a pose at a x value of 2 and a y value of 2 and whatever rotation. And then it goes to x equals 6 and y equals 4. And that is the trajectory generator. You can add new poses in there and cause the robot to follow a particular trajectory going through some waypoints, kind of like in your navigation on a GPS in a car. Okay, let's see what this looks like. We're going to use the command palette again. Once you have a simulation, we use the command palette to simulate the robot. And if you don't find it, you just type in simulate and it'll come up fairly quickly on the list. And then you've seen me doing this already. Just check each of these extensions and our simulator will come up right now. Okay, when a new simulator comes up, we may have to play around with it a little bit. First of all, I'm not seeing our keyboard connection here. Keyboard 0. So we have a simulated joystick and we're going to use the keyboard to act as that joystick. So we put this here. There we are. And I believe that's WASD, yes. So A and D are moving back and forth on axis 0, and W and S go back and forth on axis 1. So I just dragged a keyboard 0, onto keyboard or joystick 0. So the keyboard is being used to emulate the joystick. And there we are. Since that's now running, I could operate this in teleoperated mode. Now, where is my robot? It's not showing. I need to show the field. So I should be able to go through the network tables and show under the smart dashboard the field. So it doesn't show up by default. I can make the field a little bigger so that we can see what's going on. And I can crunch down some of these windows and just keep them off to the side somewhere. Don't really need them. There, our field fits nicely here. And I'm not sure if by default it runs in teleoperated mode. I'm going to try. It does. It just runs forward and backwards. It does not turn by default. Well, we can fix that fairly quickly. Let's see what it does autonomously by default. It has a little routine. Turn a little to the left and turn a little to the right and then stop. Okay, so that's our basic robot simulator. Now, when you simulate it, you might want to try running it in teleoperated mode, but by default, it's only going back and forth. Let's see if we can fix that in the code. It should be down here under autonomous, or sorry, no, teleoperated periodic. Here we go. Oh, yes, it was actually using a right-hand controller. So I changed this to left before so that both the forward, backwards, and left and right are coming from the same left-handed controller, which is the first one. Hopefully that's enough to actually run on the simulation and get it working. Okay, let's try teleoperated and WASD. Now it's able to turn. with WAS and D as those commands. And autonomous, of course, works here. It's going to start from the default location and do a little routine. Let's see if we can make it do a little more in its autonomous routine by changing the trajectory. I'm kind of thinking out loud as I do this. I haven't done this in a little while. Let's try to make that 10 and 1. Make one more. And make this one 1 and that one 10. See what happens. Not sure at all if this is going to work because I was playing with this a long time ago. And well, we'll see if it's going to work here. Just take that off and try again.
There's an error
Oops,
on the
my
generator
build
trajectory.
failed. So, oh yes, it's looking for the interior, the starting pose, the ending pose, and then there's a list of interior waypoints. So maybe it needs those in here. Still doesn't like what's happening here. I know in a previous session, we got this working fairly reasonably. I may just take one of these points out and see if it will work. Otherwise, we may have to sort of bail on that. There is one of the previous sessions where we did get this working, so you may want to refer to a previous session. As I'm seeing it right now, it is not liking what's happening. So I think it has to do with this. We may have to actually define these as points in a different way instead of poses. So we could come back to that. We may be able to find that online. So the best that I can do is just change its start and end points, 10, 1 and 1, 10. That's going to be okay, I think, and we'll try that.
What are poses?
Poses are a X and Y position and a rotation for the robot.
And
So it's
that's
like you're
for
doing
auto, right?
choreography. At like time 0, you're like this, and at time 5, you're like that. You're giving 2 different poses. Let's see what you'll see here. Hopefully, when I run the autonomous, it's going to start at a different and end at a different location now. Yeah. It started at some other coordinates and headed back to 110. It was at 10.1 and then headed back to 110. So that's what I did by changing these numbers. And could probably keep it on the field by making that 5 and 5. So with a little research, you can put some waypoints in there. I don't think it's that difficult. Just have to find the right. Oops, I took that field right off there. There we are. Try that again. Autonomous. There's 5.1 and there's 1.5. There we are. It seems to want to have a default rotation in a certain direction. Not sure why it's doing that. Some more exploration in that part of the WPI lib manual will help to reveal that. So there's a little bit of homework to research how to put some waypoints into your trajectory generator as one of several things to do to get your code working. So there we are, just checking the chat here. Good, glad that was helpful. And there we are. So that is the sort of the conclusion of the planned out portion for the evening. There may be other questions about other programming concerns. Very glad to speak about those now.
over the weekend, I was like trying to like to connect the robot to driver station, but like only like the actual like controller was connecting, not like the robot or the robot code.
Ah, okay. We were kind of troubleshooting that before. So you got the driver station installed, didn't you?
Yeah, I did. I got the
And
2022 version.
okay, and were you able to configure your team's number?
Yes,
Okay. This was with a simulated robot.
it was like, remember I have like the Rami robot.
Oh yeah, the Romy. Yes, that's right. Okay.
So yeah, I have like my team number on it,
Okay.
but like the only thing that actually connects is just like the controller.
Hmm.
It's just
Oh,
like the game controller. Like it,
oh, but the code is not compiling correctly, is it?
yeah, the code is not compiling and the communications is also red.
Okay. So there are a few things to look at. Since the communications is red, it may be that the code is fine, but it's not connecting properly. So have you configured the does the Romy have a default sort of wireless SSID or wireless network? For example, when we turn on our robot, now I've
Yeah,
never
it
used the
does.
Romy
It has a
before.
Wi-Fi network of its own.
Yeah, and are you able to connect to that with your laptop?
Yes.
Okay, so it connects on that level. And then, but the robot is not communicating then.
Yeah, like I'm not sure like if I did like a step wrong in terms of just like actually like uploading, like in terms of like transferring the code from like the computer to robot, or
Yes. Oh, well, I can go over how I would do that on mine, and maybe this will help to sort of explore that possibility. Let's say we wanted to upload this code. Let's pretend that was Rami code. If we go here to these three dots in the top right corner, we should be able to see here deploy robot code, Shift F5,
yeah,
another way. So did you try deploy?
yeah,
And did it give you a success or
it did.
failure message?
It gave me a success.
Okay, so you successfully deployed. Wow. So
And do I
that,
need to have like driver station open like a while, like before I actually press the button?
not necessarily. You can deploy as long as you have a network connection, like you're signed on to the robot's network. I remember last week we were having a little challenge sharing your screen. Is it possible to try sharing the screen again?
Yeah, I can share my screen like now. I don't like, since I'm not connected to the robot, like the only reason like why I was not able to was because like the robot does not actually give me like does not give me access to the internet. Like if I
That's
connect to
right.
that Wi-Fi,
Okay.
it only gives me access to like the 10.0.0.2 website.
Okay. Well, can we take a look at your robot setup on your laptop? Maybe we can identify something through that, and then maybe you can go offline or off sharing again and just try it again. Maybe we can
Okay.
share your screen because we can go through a list of troubleshooting items that are very common.
I currently do not have the robot now. Like it's with like a friend because like he's trying to fix it.
Okay.
So yeah, I could base like what should I like share my screen for?
But even if you share your screen, let's just double check some of the settings in your driver station.
Okay. I'll Can you see?
Yeah. Okay, so we see the driver station is there. And I know we've talked about this, but this can always be helpful. Down on the left-hand side, there are 5 buttons. The settings is the third one. I believe that's where you enter your team number, 865. Oh, have you tried 0865?
Yeah, I tried that last time.
Okay, just making sure, because it may be a 4-digit number. Okay, and then we go down to the USB.
Like before, like last week, like it had it as 0865.
Okay. And then how about the USB, which is the 4th button down? So we would estimate that when you're working on it, you've got your Bluetooth connected and the communications is off, the robot core code is off, but your joystick was on, right?
Yes, correct.
Okay. Now, what about communications? Does it give you a list there? There's some more detail on the diagnostics page.
Not sure what that is.
So maybe we can just look that up. Oh, actually, it may be the diagnostics page of the driver station.
How do I get to that?
Let me just see this. I think it's one of the tabs there. Here we are. There should be a diagnostics page here.
Oh yeah, and this was like an error code that I was like receiving. FRC, the driver station has lost communication with the robot.
Ah, okay. Okay, the diagnostics tab, which is the second of those tabs on the left-hand side.
One?
Yeah. Let me just double check that as I come back here to Zoom. So the second one down, and then that should show you if you're actually connected. And that should help you hopefully troubleshoot that. There's also an option to reboot the Roborio. And I found that occasionally solves issues, and rebooting the computer is another way to solve issues.
Just like restarting?
Yeah. There could also be something with your computer's firewall. Maybe it can sign onto the Wi-Fi, but it's not allowing traffic in a certain configuration. So you may have to remove your Windows firewall, or, well, that's not a very good practice if you're on the internet. It does work to just test stuff, but another way to do it is to introduce a permission for certain apps to connect over Wi-Fi. And so that is something that we've also had to do in the past. So you may want to double check that your computer's firewall. You may, if you're not on the internet, you can just try taking off the firewall as long as you're not on the internet, and just see if that's one of the issues, because your computer's security policy may be, oh, well, I'm not allowing traffic to that, especially through this app on that Wi-Fi.
How would I do that?
So I'm not sure which firewall you have. Do you have a firewall? Is that what the firewall there?
This is like McAfee.
Oh, McAfee. So McAfee definitely could have something to do with it. And you may want to temporarily disable McAfee. That's really not a good idea if you're not on the internet. I repeat that.
Yeah, it isn't a good idea.
But if you're not on the internet and briefly do that, you can also, I'm not familiar with McAfee, but you may have to look up how to introduce a security exception for your driver station to be able to communicate online through McAfee. And if not, Windows on its own, Windows Defender, has those kinds of security exceptions available. Do you have Windows Defender on your computer, for example?
There it is.
Maybe we can just go there. Maybe you're not using it, but it might give us an example. So let's see what we see here. Allow an app or feature through Windows Defender Firewall. That's the first one there. So if we go to that one, I think you can, private networks. Oh, there you see McAfee Personal Firewall is actually managing that. So you might have to do it through McAfee, but that's where you would have gone had you not had McAfee.
Okay.
So hopefully that'll get you on the right track, and maybe on a future session, you can have your Romy available and you can try that.
Yeah.
Good. Well, hopefully that'll get us a little bit closer. Another interesting thing, as you have that open on the right-hand side, something that I didn't know for quite some time, there are 3 other buttons on the far right-hand side of your driver station.
D3?
And yeah, and we can take a look at the voltage of our battery, for example, and some messages and charts and things, and they can be very useful in troubleshooting. So it probably would not be useful unless we have the Romy or another robot actually running, but those are good places to look to try to troubleshoot.
Thank you.
Great. So hopefully that's helpful. I see we don't have so many questions in the chat. Always happy to answer questions by email in the meantime. And if you have special or requests for topics, very glad to do that. I have scheduled for next week PID once again, and we may be able to explore PID in another context, for example, but also very happy to explore topics that you forward. So with that, we may conclude our call for this evening.
Can you talk about like autocode, like in the future, where you can like how to like successfully like make it? Because I think
with auto,
yeah,
yes, and we can go through several. I think we have several upcoming sessions that would do that, and maybe what we could do is design an auto routine that would not only move off the line, but maybe turn to a certain angle, move forward, and maybe make a little state machine in the next few weeks that we could imagine could come off the line, collect a ball, turn around and fire it. That would be great to do in auto because that gets you points.
Yeah.
So maybe we can try that.
Yeah, that sounds
Oh,
really
I see
good,
there's a hand up
actually.
with
Like,
Sienna.
yeah, I was wondering, you mentioned earlier about you had two thoughts on ways that the PID would be useful in teleop mode and driver control mode. What was the second one?
Oh, I think I meant two ways it would be useful, one in autonomous, the other in teleop.
Right, okay.
Maybe I was just thinking out loud and now I've forgotten. I'm not sure.
Okay. I'm trying to imagine like practical applications for like normally when we've competed, we just line up our robot in, on a spot in the direction we're going to want it to go, without really much concern about programming that directionality, as we just line it up. So if we're planning to roll off the line and then shoot into the target in 2020, we lined up our robot to, it's going to go this many meters forward and then pop the balls, shoot our three balls.
Yeah.
So we didn't really we weren't really doing much in autonomous of trying to rotate or angle or anything. We just lined it up.
Yeah, there are teams that line it up, and for the very basic getting off the line, it's basically executing a 2-second forward or 2-second backward command to get it off the line or out of the tarmac. It just turns out that it's kind of open-ended. So if you get your robot every time in the middle, for example, then you can do a particular thing in the middle that involves an exact motion. But maybe there are contexts when your robot has to behave differently. For example, there are multiple starting points available for the robot in any match. And then also with some careful forethought and design, you could think of turning around, collecting something, and then turning back around and firing it. And that happens quite frequently with certain teams
and that's because the balls are going to be in set locations during auto, right? So we know exactly where the balls are going to be at the beginning.
Yeah, well, that's one thing that's interesting. I have not read the rules in a detailed way enough yet in that section of the rules to understand whether the red and the blue balls are going to be exactly the same each time. Because if that's the case, then you don't have to identify their color. There may be one more step to say, oh, is that a red one? Oh, I'm the red team. Oh, good. Let's go for that one. Oh, it's blue. Oh, let's avoid that one.
I really hope that like the colors are just like not randomized on like where people like place them like each match, because like I think then like you might need to like have like a color sensor, like you may need to like have like a color sensor, like because like during auto, like you don't really want to like shoot like one of like the opposing team's balls because that just counts for their point.
But it actually turns out to be not so difficult to process camera feed in real time and identify the color. Like my students had that last year and the year before, and we never got to try it on the field. We finally had it, and then we never got to try it. So we wrote a Raspberry Pi routine that processes camera feed. And I have that planned for a future session. And I also did that at the Swapposium earlier in November, where we have maybe 20 camera shots per second being processed, and then the color is being pulled out. And we're asked, well, last year they were yellow. So we could identify yellow and then completely ignore all other colors and then find an X and Y value for that yellow to give us an indication as to whether we're lined up on a certain target, such as the ball on the floor. I see that Yu has a hand up. Just to continue, just to comment on the auto, and that's something we can explore, making a auto sort of routine and build it up over the next few weeks and include what we call a state machine, where it moves from state to state. Have we finished lining up? Yes. Okay, spin up the motor. Is the motor at full speed? Yes. Okay, now fire up the other motor. And so, for example, and the other thing, just to finish Yana's question, a few places where you may want to have the PID, lifting a robotic arm to a particular angle is the same perhaps as turning a robot on the floor. And it was mentioned in the chat that also firing a ball, PID is great with shooters, it said right there. So
Well, thank you.
Just a few things to remember. I see there's a question from you.
Hi, William.
Hi.
Yeah, I find I'm a parent/mentor for Rocky team.
Nice.
So I have a background of programming, but it's a very different programming compared to robotics. So it's a lot of learning curve for me. So over the last weekend, one thing we tried, we got the encoder works and the drivetrain, all that stuff.
Nice.
So far, I'm pretty happy with the students' progresses. So one thing we have tried is, which is I find that when you showed us the simulation, it happens there's a something about the trajectory.
Yes.
One thing we tried over the weekend was something the student was trying to do the characteristic. But either I guess we didn't quite understand the way it works, because you allow the robot to drive certain distance to kind of record the behavior or the drivetrain, or I'm not sure if I says precisely, but it tried to record some aspect of the robot and getting some. I'm just personally, I feel like that's something related to the KIP we're talking about. Maybe it's not, but I'm not sure how far, like when we're running that tool, like a characteristic, how big the area is. The area we have is pretty small. I don't want the robot banging on the wall or stuff.
Yes.
So I thought that the simulations actually, if it works, it would be perfect. So that's my question. And, and also the trajectory code from the simulation. If it's possible to take that part of code, put in the robot code, like using against a real robot, would that work, or there's more work to do?
Yes, the biggest work to do to translate between the simulator and the robot, and this is something I haven't used the simulator a whole lot like this. We did trial and error in my team, where we would just try a very simple thing like move forward for 1 second. Oh, how far did it move forward? And then we started using encoders, and then we measured, well, how far did it go when the encoder was at 1,000 or something? Oh, it went 2.5 meters. So we just did a little calibration that way. Now, when we look at the simulation and compare it to the robot, we do have to characterize the robot's physical features, including its mass and its gear ratios and the like. And if you can carefully research those and accurately enter them, there's a higher chance that the simulation will correspond more closely to the physical world. That said, there's always an imperfection when modeling a physical system. Like, for example, in a physics class, if you point the robot on 0.05, it'll still move forward just slowly. But in engineering class or in robotics class, if you put the robot on as 0.05 forward, it's not going to move. In practice, our robots would move sometimes only when you put up to 0.25 power. So there's a theoretical difference from reality.
Yeah, I have to agree with that because the student was trying 0 point something. It wasn't moving at all. So
Yes.
they changed to 0.8. It was
Ah.
a shootout like a bullet. So they said, oops.
Yes,
So
and
they
it's
have to
quite
lower.
steep.
Yeah,
Getting
so they have
the
to lower
exact
to
level
the-
is, whoa, it's tricky.
Yeah. The other thing when they use the tool for a characteristic, the robot was driving backwards for I think maybe for 5 meters nonstop. So we have to, every day yelling, stop, to pause it. So we're not sure what it's trying to do.
When you said driving backwards, one thing that did come to mind, it is possible to multiply the motors by -1 so that backwards becomes forwards. And that is one way to do it. You can also physically change the red and black wires. That's not always convenient or advisable, but there are different ways to adjust it so that when it's supposed to go forward, it's supposed to go forward. But yeah, as you were saying there, it's not quite satisfying. You would want it to be perfect, but actual real life systems always have those imperfections. And that really steep curve with electronic systems going from no motion at all to going way too fast. So finding the sweet spot is a little bit of a challenge. There are ways that you can also adjust the motor mathematically. So instead of going in a linear sort of way, maybe a squared equation. Some people have talked about doing squaring the input, for example, or doing some other mathematical modification of the motor so that you get a better response.
Yeah, thank you.
Oh, you're welcome.
I guess this is like exactly you explained what is in the document. For example, the motor controller modes is different than adding the friction and all that stuff. It's
Yeah. And
so,
yeah, just start simple. And you can imagine a 3 or 4 little tests that can get you up to more confidence. When we were testing our robot last year, the first time we did our autonomous, we were off by a factor of about 5 and it just slammed into the wall. But the second test, it was much better.
yeah. Well, I have to say the encoder so far it's pretty accurate, even though
Yeah.
the left and the right is slightly different. So
that's always the case.
Yeah, so it's wasn't going exactly straight. You kind of know that it's turning a little bit, a tiny bit. So yeah. But
and we also found that robots don't always want to go perfectly forward. We found it could be your wheels are too tightened on one side, or that one of the motors is not getting 100% of the current. Maybe the connection is not as strong. One way or another, it doesn't go perfectly straight. In the past, we've had times when we had to add about 0.05 to one motor to make it go straight. And things like that have happened.
Yeah, I remember that too. With encoders, or I guess motors too, but with encoders, I'm wondering, because this will be our first year actually using encoders. We managed to we have Falcons, we got some.
Nice.
I was watching the back order available. Boom.
Excellent. Bye.
Bye. And how much does the strength or the charge of the battery affect how much, like, predictability of your power output? And so
it's good to have charged batteries and healthy batteries, because even a charged battery may not be healthy. So nice to check the levels, have nice, fresh, relatively new batteries. As
So
the batteries get older, you get unpredictability and they don't charge as well. So you want to have that well over 12 volts if possible.
So if you have it set to go at a certain speed, does that, and your battery's low, then it won't go that speed?
It is quite possible. And so there are ways to deal with that. Always replace your batteries at the start of a match, use new batteries, and also be a little bit concerned about how much total power you're drawing during a match. If you're running all motors on full for the whole match, it's going to definitely affect the batteries. But if you're careful about which motors are running at what power when, then you're going to draw a little less current and have a little less of an issue with that. So I think there is a way in the software code as well to read the current battery level and maybe respond appropriately. So that gets to be a little bit more advanced as well. So maybe you could develop an equation to give it a slight boost or a slight reduction depending on the current battery charge, who knows?
Right, because at the end of a match, if you're starting to run low, you may not have enough left to, if you are current at your programmed levels, you might not be able to run your lift mechanism.
Exactly. So yeah, good things to keep in mind.
Yeah, I think in our previous seasons, I liked what you said about like when you bring up your one motor up to full speed and then fire the other one. Because I think what we were
Yes.
doing is doing our intake, our one, no, for shooting, our one motor would start spinning and so would the other one. And they were both going like gangbusters with no ball for the top one to shoot out.
Oops. And then, yeah, the first ball that comes out doesn't quite make it. That happened to us last year because we were doing it manually and we didn't quite get the ball or the motor to the quick speed. And so we only got 2 out of 3 on our, this is the last thing we're filming before the deadline. So we got 2 out of 3 baskets on our shooter.
Okay, so yeah, that would explain, because I never even occurred to me that was why the first one would not make it. It was because the motors weren't at full speed yet.
That could be an issue. Yeah, so much that can be learned from these discussions. It's really interesting how we quickly realize how life gets in the way of our grand plans. But this is where we learn to overcome the complexities of life and achieve great things together. So wow. So with that, it's been a really great time to see everyone this evening. And again, very happy to answer questions by email in the meantime. And look forward to next week. We'll do a little bit more of PID, but we'll start aiming towards some choreography routines for our robots to do some stuff automatically to get accuracy and efficiency in various operations on the field.
Good night, everyone.
Have a great night. Thank you very much to everyone.
Next week, will it still start at 7?